So this is David Nemi, and I'm going to switch gears a little bit and talk about the transportation problem. In this case, we have several warehouses denoted by the set W. Each of them has a supply of widgets, and we have a set of customers denoted by the set C. Each has a demand for widgets. And between each warehouse and each customer, there's a cost per unit of shipping a widget from the warehouse to the customer. And what we have to decide to do is figure out how many widgets from each warehouse will go to each customer. And we want to do this, obviously, with a minimum cost. So how we model this is a linear program. Well, we want to minimize the shipping cost. So the shipping cost is computed by the per unit shipping cost times the number of units that we actually ship from the warehouse to the customer. And we have two sets of structural constraints. We have to satisfy the demand, and for each of those, we have one row for each customer. And when we fix the customer, we're going to sum over all the warehouses of all the X variables, which is the amount that's shipped from that warehouse to the customer. And that sum has to equal the demand at the customer site. And on the supply side, we're going to have for each warehouse, we're going to fix the warehouse. We're going to do the inverse of what we did for the customers, for the supply, for the demand. So for the supply, we're going to just fix the warehouse, and we're going to sum over all the customers. And that has to be at most the supply at the customer site. And we have the usual non-negativity constraints. Now, what we can notice here, when I build a model, I'm going to do it slightly differently than we did the diet problem. And I'm going to notice that each X variable appears exactly twice in two constraints. It appears once on the demand side because it satisfies the demand, and it appears once on the supply side because it takes supply from one warehouse. And what we're going to do is use a Gurobi class called linear expression, and that's going to allow us to incrementally collect linear terms, so coefficient times a variable, and we can use those in constraints. Let's go ahead and do that. So here I've created some data. I pre-populated some data, and I have a cost function from warehouses to customers. So in the data, I have warehouses, and we can look at that. We have a set of warehouses, and we have supplies and coordinates. And I'm using this Gurobi utility called multidict. It takes a dictionary with values that are arrays, and it returns first a set of keys, and then a separate dictionary for each value in the array. So in this example, we can look at the supply. The supply dictionary that was created, and this is a mapping from the warehouses to the supply. And we have the same thing for the demand. So it's a mapping from the customer to the demand. And I have a cost function here, which is just simply gives if I give it an ordered pair of customer and demand of warehouse and customer, it'll give me the per unit cost of going from that warehouse to that customer. So that's just the input data. And so what I want to do is just create the Gurobi model for this. So first I'm going to create a model, and let me create a container to store the decision variables, X, which will be a dictionary. And let me create the linear expressions that we're going to use. So I'm going to create a linear expression for what gets pushed to each customer. And this will be a dictionary too. There's it'll map from the customer to a linear expression object. For each customer. And we'll also create a one for what's pulled from each warehouse. So now we can see these linear expressions contain the value 0 because we haven't added anything to them. So let's create the variables and let's also populate the linear expressions. And there's one thing I want to just do here because we're going to do it a lot. Create a list of ordered pairs of warehouses to customers. Warehouses. So this just contains the list, so I can iterate across the lanes instead of doing 2 loops. So let's use that right now. For each warehouse and customer in lanes, so what we want to do is create the variable, and we're going to store it to the dictionary. To create the variable, we use addvar, and in our case, we want to have an objective. That's going to be the cost going from the warehouse to the customer. That'll be the cost, and I'll go ahead and name it. And it'll be the name X with the warehouse and customer separated by periods as our convention. Now I created the variable. Let me go add where the variable is going to appear in the expressions. So it's going to appear when I ship something from warehouse to customer, I pull it from the warehouse. I'm going to get the pulled expression. This is a linear expression. And I'm going to use the overloaded operator plus equals. And plus equals will add a term to the expression. Now it's a coefficient. You normally will add a coefficient times the variable. In this case, it's 1, so we don't need the coefficient. So we'll add this link from the supply side, and we will also add this variable to push to the customer, to the demand side. Let me go ahead and do an update. We created the variables, and we organize them in these linear expressions. Let's go ahead and write this out to a file, to an LP file. Let's look at what we've done so far. So in this case, we created our variables. We created them with objectives, so they appear in the objective function. We don't have any constraints. So our linear expressions are just there for us to use in constraints, but they're not in the model yet because we haven't created any constraints. So let's create constraints. So we're going to create the supply constraints. So we have a supply constraint for every customer. So instead of doing a quick sum, we're just going to use the expression, the linear expressions that we used, that we created. So this is a demand constraint here. So what's pushed to the customer has to be equal to the demand of that customer. And we'll go ahead and name it with demand, and it just has a single subscript. So let's do the same thing for the supply side. Warehouses. By the way, let's go and look at the pushed expressions. See, the expressions contain now they contain actually the sum. For each customer, they contain the sum. If we sum across the warehouses, so each linear expression, the customer is fixed. We see the warehouses exactly once, and if we looked at the pulled, we'll see the same thing. We'll have for Austin, say, we have Austin's constant, and we have all the customers. So let's go ahead and let's create supply constraints. So in this case, we're going to say pulled from the warehouse. That can be at most the supply at the warehouse. and we'll name it the supply constraint. Now let's go ahead and update so that the constraints get added to Gurobi. And let's go ahead and write out let's write the LP file again, and let's look at it. So this looks like what we wanted. We have our demand constraints. The demand at customer 3 is, the demand constraint is that what's shipped from El Paso, Austin, and San Antonio has to equal the supply, which is 40, and we have the same thing, S equal demand, which is 40. And on the supply side, we can see the what we ship out from, say, El Paso is at most 90, which was the capacity supply at the El Paso facility. So we have that. Let's go ahead and optimize. Let's go ahead and solve the model. We're pretty sure that we have the right model. Our code did what we expected. So we optimize. We get a value of 7,170. Let's go ahead and just save that. We want not just the objective value, we want to see where did we ship things. And what I want to do is just say, where did we actually ship things? And I don't want to print the zeros out. And what I'm going to do is, rather than comparing to 0, I'm going to declare a small constant, epsilon. And what I want to do is print only the values that are greater than epsilon rather than greater than 0. And that's because we're dealing with floating point numbers, and often we'll see small values like 10 to the negative 10th creep in, and they're considered, they're practically 0. And by default, up to a certain tolerance, Gurobi considers those values 0. You can set that tolerance if it's an issue, but normally defaults are pretty good. But it's good to not do comparisons to exactly 0 when you're dealing with floating points if you want to see something is 0. So let's go ahead and look at the non-zeros. So we had the variable X. We want to look at the lane, which is the customer pair. We want to look at the value of X. And the variable is X, and the attribute on the decision variable is X. We want to say for ln lanes, for each lane, but only if the decision variable is significantly greater than 0. And we can see what we have here. So we can see our results. So not only we have the cost, but we have what we should actually do. Now looking at this, we can notice one thing. Everything's integers. And that's actually not an accident. The model we had was something called a pure network flow model, and it had all integer data. So the values are integers. It's a nice feature. It's obviously not always the case for MIPS, but it's a nice feature for us. One thing we may notice also is looks like most of the warehouses, most of the customers receive their deliveries from just one warehouse, except for customer 4. Customer 4 receives 30 widgets from El Paso, and it receives 50 from San Antonio. He may present this result to, say, a business sponsor, and may say, well, wait a minute, we can't have this. The customers can't be receiving partial orders. It creates all kinds of headaches. And so you have to come back and say, well, how would we change that? How would we fix that for them? So let's go and talk about how to do that. So we want to look at the business problem, which is each customer can receive widgets from only a single warehouse. We can do it in a lot of different ways. We could just do what we did, similar to what we did for the diet problem, add an indicator variable. Let's say we add an indicator variable Y on the lane, and it would be 1 if a customer receives any widgets from warehouse W and 0 otherwise. Add a constraint that would say if we sum over all the warehouses for each customer, that has to be 1. And then we need to actually enforce this definition. And we can do that with this type of constraint. We can see this. We say XWC is less than or equal to demand at the customer times the indicator variable for that customer. in that warehouse. Now, if YWC is 0, we will see XWC has to be 0 because the right-hand side will be 0. And if YWC is 1, XWC can take on any value up to the demand. And that's fine because we know that we're never going to ship more than the demand to any customer. So effectively when YWC is 1, X is effectively not constrained in any way. So this is a common thing when you're creating indicator variables like this. You need to come up with a coefficient on your indicator variable that's small enough, that's small but not too small so that it artificially constrains your continuous variable. So that's one way to do it. Another way you might notice is to say, well, if every customer is shipped just from one warehouse, then I know whatever shipped has to be exactly equal to the demand. So you could just do a substitution. Everywhere you see XWC in your model, you substitute it with demand times the indicator variable. And then you still have to have the indicator variable. You have a pure integer problem. Another way you could do it is actually use the semi-continuous variable type on X. I encourage you to look that up in the documentation. I'm going to do it a little differently and use maybe what's a little bit more in the corner of Gurobi, and it's the special ordered sets. And it's an interesting, effectively a constraint that can be very useful if you need it. It's not necessarily the first thing you should look at, but I want to show it to you anyway because I think it's useful when you do need it. And what this says is, at most, the special ordered constraint takes a list of variables, and it says at most one variable in that set can be non-zero. And these can be integer variables, they can be continuous variables. And so what we want to do is add a constraint, and there are two types of special ordered sets. What I'm talking about here is special ordered set type 1. There's also a type 2. And what we want to do is basically say we want to have a special ordered set of type 1 on all the XWC variables for all warehouses for a particular customer. And to do that, we're going to use this add SOS, which is a function on the Gurobi models. And the parameters, the first parameter is the type, and then the second parameter is the list of variables. Let's go ahead and do that. So what I want to do is add for every customer, I want to add the SOS variable, SOS constraint, and it's going to be type 1, and I want to have the variables. So I need a list of the variables that I'm going to use. It's going to be X of W, C, for W and warehouses. That's it. So our for loop is for C and C. So the C is coming from the for loop, and the W is coming from our list here. So now we have our SOS variables. Let's do an update, SOS constraints. And let's just go ahead and let's write it out and see what it looks like. So we haven't changed any of our structural constraints really, but we have a new section called SOS, and we have our SOS constraint here. We can see for C3 we have, for customer 3 we have the 3 warehouses, and the newest one of them can be 1. So let's go ahead and optimize. So we run this again, and we get 7,100. Let's look at the difference, by the way. So we have an extra cost of 590, and so it's an extra 8% higher cost. And we can actually go ahead and look at our lane activities here. And I can see we have just every customer receives its shipment from just one warehouse. So now we can do that, and we can let the business know that this policy is costing an extra 8% in shipping costs, which may be fine, might not be, but at least we can quantify that. So this is another useful feature sometimes for doing optimization models, is to actually just evaluate what the effect of certain policies might be. Okay, so let's conclude up the transportation problem, and we can see there's a lot of ways to model a given business problem. And there's several ways for a specific model to put it into Gurobi, and you can use whatever is the most convenient and easy to build and easy to maintain and most intuitive way possible. There's also something we didn't use, which is the column object. Specifically, we looked at using QuickSum and building constraints that way, and we also looked at using linear expressions and building constraints based on those linear expressions. There's also a column class in Gurobi, which is way after you've already built the constraints. You can add additional variables later on. There are a couple of Python utilities that are applied by Gurobi, multidict, which we looked at a little bit. And there's also a tuple list and its select method. There's also a really useful way. I encourage you to look at that, especially if you're looking at more complex relationships than just every pair, like we had in our example. And maybe you noticed I used something called IPython, which you can use. It's nice for interactive work. If you want to get the features of the Gurobi shell, you just have to put this line from Gurobi Pi import star, and you get everything in the Gurobi namespace in your global namespace. And you can treat it pretty much just like Gurobi Pi. And you can get it from python.org. It just lets you know that you can use all of the Python features, maybe particularly for people who are familiar with it. And that's nice. So thanks for watching our screencast and webinar.